I'm extremely happy to introduce our speaker today, Dr. Benjamin Shaby from Colorado State University. Dr. Shaby got his dual bachelor degree from several universities in mathematics and English. And then he got his PhD degree in statistics from Cornell University, co-advised by David Rupert and Martin Wells. And then he did one postdoc at Stanford and another postdoc at Berkeley University. And then he joined Pennsylvania State University as an assistant professor, and then he got the tenure there, but he decided to move to Colorado State University in 2019. So he has got the Career Award from NSF and the Young Investigator Award from ASA. Dr. Shaby has done many superb methodological and applied works in spatial statistics, with application to the modeling of extreme weather events and maybe the analysis of high throughput data in biology. So let's welcome our student.
Thanks for the nice introduction. It's great to be here. This is my first visit to College Station. And as you just heard, I spent a few years at Penn State. And when I told people I worked at Penn State, the first thing people always said, almost invariably, is, "Oh, College Station." And that's not right. And so I sort of wondered what all the fuss was about. Now I'm here, so it's great to be here. If someone can explain that to me, I would appreciate it, by the way. I never understood that. Penn State's in State College, Pennsylvania. Anyway, I just noticed the date. Today is my sister's birthday, so I would also appreciate it if someone could remind me after the talk. Great. I need to call her and wish her a happy birthday. I don't want to forget that. Okay, so on to the talk. So this is work with Likun Zhang, who's an assistant professor at Missouri now, was a postdoc with Mark Risser at Lawrence Berkeley National Lab. So the title's a little bit weird. We're having trouble coming up with the title. So scale aware. This is really scale dependent dependence, but that's too many uses of the word dependent. So there's sort of no good way to say this. But hopefully I'll try to explain to you what this means. Scale aware dependence modeling for dimensional spatial extremes. Okay, and so I think the easiest way to set this up is with a concrete example, and precipitation I think is the sort of most intuitive. That I always come up with anyway. So what you're looking at here is a map of the continental United States, and these dots are rain gauges. Okay, so this is in a network of climate data. They aggregate all the data from these different gauges, and so I mean. The reason why we might care about precipitation data, at least in the extremes context, is for inland flood risk assessment, right? Essentially, if enough water comes into a watershed quickly enough, it exceeds the watershed's capacity to drain it, and you get a big flood. And so this is something that we care about. And obviously, the extremes are the important aspect of the precipitation process, right? If you don't get a flood, if you don't get a lot of rain, right? You need a lot of rain. You get this clear interplay between the intensity and the spatial extent, right? If it rains in a very intense way in a very small localized area, you don't get a flooding problem, right? But on the other hand, if it rains maybe not quite as intensely over a much larger area and maybe the entire watershed, then that can pose a risk. Okay, so the interplay between the intensity of the process and the spatial structure of the process is really important. Okay, and so if we want to model over a large area like the continental United States, obviously there's a lot of heterogeneity in the precipitation process, right? And so we want to be able to model the important features of the joint tail of this process over a large complex domain. Okay, and so one of the ways we summarize extremal dependence is with this this coefficient chi. So usually in spatial statistics in the Gaussian process world, the thing we're used to talking about is the correlation or the covariance, and that's sort of not the right thing to talk about in the far tail, right? Because the definition of the covariance is sort of the propensity for things to vary from the mean together. But we're not interested in the mean, right? We don't care about the average precipitation at all. This is not what we're studying. We care about the tail. And so this is the correlation of the covariance is sort of not the right thing. And so we've come up with these various measures of trying to understand the dependence in the joint tail, and a popular one is this thing called chi. And so what is this? If we think about the precipitation at two locations, we'll call that x1 is a precipitation at x1 and x2 is a precipitation at x2. This is just a conditional probability. So what we're going to do is apply the CDF at location x1 and the CDF at location x2 to bring things to common marginal distributions, right? So we want to get rid of the marginal characteristics and just focus on the dependence. So we're going to apply the CDF. This is just a probability integral transform. So now we're on a uniform scale, and we're going to say, well, okay, given that the precipitation at location x2 or location 2 is large, what's the probability that the precipitation at location 1 is also large? Okay, so this is sort of measuring the propensity of extreme events to happen at the same time. Okay, and then often what we'll do is take the limit as u goes to 1. So this is the limit as we get to the upper endpoint of the distribution, which could be infinity. Okay, so if we take the limit as u goes to 1, this is well, how often do the most extreme possible precipitations happen at these two events, these two locations at the same time? Okay, so this is chi. And if we, so this is just a conditional probability, right? We can measure this empirically. We can just count. Look at all the times we have an exceedance at location 2 and count the number of times we also have an exceedance at 1 and do this for higher and higher thresholds. And so what you get, so we've sort of limited the, I don't know if you can see, this is what we're calling the Great Plains region, maybe expansive definition of Great Plains, but so we're somewhere down there, right? And up there is Canada. The borders may be a little hard to see, sorry. So we sort of empirically estimate this conditional probability, and we get a curve like this. So what you can see is that when two stations are distance h small apart, so h is the distance that these stations are apart. So when they're close, we get pretty high extremal dependence. 0.5 is very high. Okay, and as we'd expect, right, when the stations get farther and farther apart, this thing decays. And it turns out that the rate at which this decays as we get to the upper limit, to the upper endpoint of the distribution, is really a sort of important thing that we're going to try to capture. Okay, so this intuitive behavior where we have strong extremal dependence at close ranges and it weakens at longer ranges is something we definitely want to be able to capture. Okay, and so what happens if we move that threshold up a bit? So that's what we're seeing in these different colored curves. Well, the extremal dependence weakens as we move the threshold up a bit, which also maybe seems intuitive, right? If I don't know if this seems intuitive to people or not, but this is actually a behavior that we can't capture with the sort of classical extreme value spatial models. So what happens with the classical models is that once you get to a certain threshold, we don't get weakening dependence. And clearly in the data, we get weakening dependence, right? This blue curve is definitely higher than the red curve, definitely higher than the green curve, right? So we want to be able to capture this weakening dependence as we move to a higher and higher threshold. Okay, and so that's what we want to show here is empirically, we can look at this alternatively. We can fix the distance that the stations are apart. Here, we're fixing the distance at 60 kilometers apart and look at this, this dependence measure as a function of threshold, and you can see it's clearly decreasing. Now, an interesting feature of this plot is that in extreme value world, we sort of care about what's happening over here beyond the range of the data, right? So this is the 0.99 empirical quantile. We want to understand what's happening at even higher quantiles. We want to know the once in 10,000 year flood. And obviously we don't get data, right? But so we want to understand the behavior of this curve here. And what we're going to see is that there's sort of two classes of dependence models. One class where this limit goes to 0, one class where the limit is non-zero. And traditionally, we'd have to use different models for those. And the troubling aspect of plots that we see from empirical data all the time, it's really hard to tell whether this is going to go to 0, right? Like, there's considerable uncertainty in the tail, sort of by definition. We don't get a lot of data there, right? So is this thing going to keep going down, or is this going to level to a non-zero model? And this is traditionally has been a choice we've had to make. We've had to decide whether we think this is going to 0 or not. They're going to imply different models. Okay, something else we need to worry about is that the tail dependence might be different at different locations throughout our large domain. And so what we're going to see here is a sort of moving window estimates of that same coefficient of dependence. So these black rectangles represent the moving window. So at every one of these blue pluses, we're going to estimate that coefficient of dependence, and we're going to do it in a window the size of that black thing. We're just going to move the black window around and see what happens. Okay, and so here's what you get at threshold 0.9. So at 30 kilometers, this is the coefficient chi, and so you're seeing, I don't know, I would say somewhat convincing evidence of heterogeneity, right? This is chi 0.5, which is really, really strong dependence. We're seeing much lower in other areas. So it certainly looks like, at least at threshold 0.9 at distance 30 kilometers, we're getting different strengths of tail dependence. So as we move that threshold up, we see even more heterogeneity. And if we bump it up sort of like as high as we can reasonably go for just an empirical estimate, we see something like this, where the dependence remains really, really strong. So just as strong here at threshold 0.99 as it was at 0.9, right? So it sure looks like the tail dependence is decaying much slower here than it is, say, here, right? So we need a model that's going to be able to capture this spatial heterogeneity. Okay, and something I'm going to gloss over here is the marginal behavior. So at any one of these rain gauges, we really do care about the marginal behavior. This is really important. But this is not what we're focusing on. We're focusing on dependence. So we're just going to consider this a solved problem. We're going to say, okay, we know how to estimate marginal extreme value distributions. Whether you believe that or not is a different question. We're just going to assume it and say the thing we're going to care about here is the dependence. And so the way we're going to approach this is with a Copula approach. And this is just a marginal transformation. So what we're going to do is at every spatial location, we're just going to assume we can transform it to uniform. And it turns out we don't lose any generality by doing this. Every spatial process, no matter the margins, no matter the process, has an equivalent Copula representation. So this is sort of in full generality. This is just a convenient thing to do, so we can focus on the dependence rather than the margins. Okay, and I sort of hinted at this before, but there's a sort of bright line difference between models where the limit of this dependence coefficient goes to 0, and so the case where the limit as we go to the upper endpoint is 0, and the case where it's non-zero. Okay, and so traditionally we'd have to choose a different model. So we really want to be careful about whether we think this model is asymptotically independent or asymptotically dependent. And so does this chi measure go to 0 in the limit, or does it converge to something that's non-zero? Recently, we've discovered that this is not as bright a line as we thought. So for a very long time, we thought you have to choose a priori. We need to decide, do we want an asymptotically independent model or an asymptotically dependent model? A very important advance in the last, I don't know, 5 years has been, well, okay, maybe we can design models that can transition according to a parameter that we can estimate from the data. And so that's great. The thing we couldn't do until even more recently, I would say, are these features that I pointed out. One, we want the dependence to be able to vary across space. This is the sort of thing I pointed out. We want spatial heterogeneity in the strength of tail dependence. This first bullet point here, we want to be able to have the dependence class depend on distance is something I haven't mentioned, but actually really important for things like precipitation. So at least in parts of the country where precipitation is dominated by convective systems, like thunderstorms, like here, right? A question?
The last slide, there is U1 to UD. Each quantile of the part is different U1 to UD. But the other slide is the same U. So my concern is this kind of correlated extremal value event, this situation. Many times one region has extreme values, the other regions maybe it's a less, it's a smaller value on that, not the same value. And as this is the general case, but the other relationship, all the same value of U, right? That's my concern.
Right. So yeah. So these are sort of different things. So this is the chi measure. So this is the same U, right? So this is like if we have an exceedance over some high level, what's the probability of having exceedance over the same high level? But remember, they're both on the uniform scale. So we've transformed the margins. So this U is sort of like the level of extremeness, and it's relative to the local marginal distribution. Here, this is the CDF of the process, right? So this is sort of like
The multivariate distribution.
this is the model, right? This is the model here would be C. This is the multivariate distribution after we've transformed the margins. So this is different than chi, although they're both probabilities. But yeah, absolutely, the scale of what it means to be extreme at location 1 is going to be different than what it means to be extreme at a different location, and they're not necessarily going to be extreme at the same time, which is sort of what we're trying to model.
Thanks, sir, for the question.
Yeah.
Is there any specific type of copula that you're using?
Oh yeah, that's the whole game is to figure out what type of copula to use. Yeah, that's right. Okay, so we have these two dependence classes. It turns out we can design models to transition between them. There's this other feature that we want to be able to build into our model, which is have the dependence class to depend on distance. And this is a little bit subtle, right? So imagine you have a process that's something like thunderstorms, where you have these localized events that are extreme at the same time, right? You have a thunderstorm. It's like rain gauge here, maybe the same thundercloud system, right? And they're extreme at the same time, but just beyond that, the extremes might be unrelated, right? And so it's really important to be able to capture this sort of like local scale versus large scale behavior, where at close range you may have very, very strong tail dependence, which might be an asymptotically dependent regime, but at slightly longer scales you might have asymptotic independence where the tails aren't as related. Okay. So this is the big thing that we couldn't do. Okay, and so I sort of, this matrix is a little bit hard to read, but I couldn't figure out a better way to display this. So we want to have scale separation. So we want to be able to represent short range asymptotic independence and long range asymptotic independence. So maybe we have a process that's just asymptotically independent at all ranges. Okay. We might also have a process that's asymptotically dependent at all ranges. So this would be something like a heat wave process behaves like this. Okay, this row would be more like a thunderstorm, where at short ranges we have very strong tail dependence, and at long ranges maybe it's much weaker. And then this last case kind of doesn't make any sense, at least not for any system I can think of, where at short ranges you're asymptotically independent, you have weak tail dependence, but at long ranges you have very strong tail dependence. You maybe can convince yourself there's some teleconnection situation where this might happen, but it's sort of not super important, at least as far as I'm concerned. And then kind of separately, we want to be able to have this strength of tail dependent varying with space, as we saw in the picture of the Great Plains, right? So we want all of these features. Okay. So what can we do? Well, it turns out we got a long way by considering this class of models that's just based on Gaussian processes. So this is transformed Gaussian scale mixtures. So if you're familiar with Gaussian processes, this should seem very familiar. So the way this works is we take a standard Gaussian process Z. Maybe we transform it with a link function. So this would be, just like in GLMs, you have logit or something like that. So pick a convenient link function, and if you're clever about this, you can get some nice properties, and then just multiply it by univariate random variable. Okay, and then So it turns out that this very simple construction allows us to get lots of different tail dependence characteristics. And the key thing here is the relationship between the tail weight of this transformed Gaussian process and this univariate random variable. So you can think of these things as kind of like fighting. So if the tail of R is heavier than the tail of G of Z, and then we get asymptotic dependence. And if the tail of G of Z is heavier than the tail of R, we get asymptotic dependence. So the intuition, at least the way I like to think about this, is that, well, a Gaussian process has extremely weak tail dependence, because weak as we can get. Not so weak, it's not realistic for probably any process that we'd ever see. Okay, so if this transformed version of this has a heavier tail than this, then the tail dependence from this part wins, and we get really weak tail dependence. But the univariate random variable has perfect dependence in space, right? It's just a single random variable, so it's completely dependent. And so if this has a longer tail, then the dependence from this complete dependence wins. Okay, so we're sort of balancing this perfect dependence and this very weak dependence. And the thing that determines who wins is the relative thickness of the tails. Sorry, and just a little bit of notation. This is the survivor function. Okay, so this is how thick is this tail as we go to infinity. Okay, and then if we're clever about this transformation G and we're clever about the distribution of R, we can design processes that can transition between R winning and between G of Z winning. Okay, and there was a bit of a literature on this a few years ago, and so the first extreme focus version of this was a paper in 2017, and they let R be this sort of Weibull-like distribution, and then as this parameter phi goes to 0, it's a Pareto-like distribution. So here we have a heavy tail, and here we have a light tail. Okay, so for all non-zero values of phi, we get an asymptotically independent process, and as we take the limit as phi goes to 0, we get an asymptotically dependent process. This is great. This is uncharted territories as of 2017, right? So this is a process that can transition between asymptotically independent regime and asymptotically dependent regime. The problem with it is that we only have the asymptotic dependence regime at the edge of the parameter space, which is kind of inconvenient. A couple of years later, we had this process that can transition in the interior of the parameter space, and it's a little more complicated. So up here, G was the identity function, so it was a little bit simpler. Here we have a non-trivial G, and what this G is a marginal transformation from standard Gaussian to standard Pareto. Okay, so what it's doing is it's putting G of Z on a heavy-tailed scale, so that R can kind of compete with it on a fair playing field. That's the way I think of it anyway. So this is great. So we can transition between very weak tail dependence, very strong tail dependence. We can get things that look like Gaussian processes all the way to things that look like very strongly dependent processes like max stable processes or generalized Pareto processes, if you're familiar with those. And we transition in the interior of the parameter space. So it makes everything really nice. Okay, and so what do we like about this this framework, this Gaussian scale mixture framework? Well, okay, we can transition between these two dependence regimes, which is really nice. And we can also leverage everything we know about Gaussian processes. So we're really good at working with Gaussian processes. People in this room have contributed a lot to this literature. So we're good at computing, we're good at modeling. So we can leverage all of that. So if we put that into this matrix, this is what we get. We get these first two rows where we can have a process that's always asymptotically dependent or always asymptotically independent, which is something we couldn't do before. So this was a huge advance. However, it doesn't have the scale separation property. So we can never get something that's asymptotically dependent at short range, but asymptotically independent at long range. Okay. And the other thing we can't do is we can't have tail dependence that varies spatially. This is a stationary model, but it's kind of worse than that. Even if we have a non-stationary Gaussian process, we still have a single kind of tail dependence. Okay, so we can't break that. So people have made some progress to try to eliminate some of these shortcomings. And so there was a paper recently by Daniela Castro-Camilla and Raphael Husser. They kind of tried to address this. And so here's this is the same model, except we get this parameter phi in the exponent here, but it does the same thing. So phi modulates the tail weight of R. Okay, so it turns out if you have a Copula model, so this is a Copula model. If you have a Copula model and you apply a monotone transformation, you've done nothing to affect the dependence. Okay, so what they did was they took logs. So this is just the log scale version of the above. And it turns out Pareto, if you take the log of a Pareto random variable, you get an exponential. And so that's what that is. And so now we're making this tail weight factor, this parameter that affects the weight of the tail in our scaling factor. We're making this vary according to space. Okay. And so this is nice. It eliminates this one problem, right? Now we get spatially varying tail dependence. So that's good. It turns out if you work out this chi coefficient, you get this thing, which details aren't important. The important thing is this part where it's bigger than 0. So this is asymptotically dependent everywhere. Okay, which is not great. So we sort of lost this ability to transition between asymptotic dependence and asymptotic independence, right? In the previous version, we had a check mark up here. What we've gained Oh. Sorry, this should have been a check mark. So this is what we've gained. We've gained this ability to vary spatially. Okay, we still don't have scale separation. Oh yeah, I totally goofed this up. Yeah, so this, no, this is right. So it's only asymptotically dependent, never asymptotically independent. We don't have scale separation, but this should have been a check. So we can.
Marks change. So how can you change the marks?
Why should it have changed?
Yeah.
Well, so yeah, so this X I'm trying to represent, though, well, this model can't do this, but it can. Like this was the whole point of the model, was that the tail dependence varies spatially. So the thing we've lost is the ability to transition between asymptotic dependence and asymptotic independence. And basically the reason is because G is in this model is the identity function. So this is always light-tailed. So this part is always heavier tailed than this. This is a Gaussian process. So if they had transformed this to a heavier tailed margins, they probably could have gotten this a transition between dependence and dependence classes. But they didn't. Okay, so there's even more recent attempt, which is so this is a little bit annoying. This just appeared on the archive, and it's very similar to our approach. So they kind of beat us to this a little bit. So again, here's the the scale mixture construction, and so they use a spatially varying distribution for the scaling factor. So this is a lot like the previous one. The thing that they've added was, okay, so this is really complicated. The important thing is that, okay, so we're doing a mixture of random variables called S, and the way they're mixing them is with compact kernels. Okay, and so the idea is that if you have two locations that are within the same compact kernel, you can have strong dependence, and if you're not in the same compact kernel, you can't have strong dependence. The thing they're mixing, though, are these S's, which have the same distribution as the HOT process, and so they're going to run into problems with the transition between dependence classes being on the edge of the parameter space. And so that's exactly what you see, and I kind of like didn't exactly know how to make this matrix. So if you estimate the parameter of that HOT process, right, that tail parameter, if you let it go to 0, so this is the star, so this is like kinda. If you let this go to 0, you can get asymptotic independence at close range, asymptotic independence at long range. Okay, you can. This is really, if you don't let it go to 0, it's an asymptotically independent model, and you can never get all asymptotic dependence. The kind of like the tricky thing. Oh, and it does vary spatially, but only kinda. So this is like a, I don't know what to call this. It's not exactly a stationary model, so you do get spatially varying dependence, but it's only because the kernels are not, there's not an infinite number of kernels, right? So it's kind of non-stationary, but not in an intentional way, kind of in an incidental way that you can't really control. So what they actually did in the paper, though, was they fixed this parameter at 0. So they do get this behavior, but not this behavior. So it's a little bit funny. So they fixed this phi parameter at 0, so they're always asymptotically dependent at short ranges and asymptotically independent at long ranges, which is great for precipitation, but not so great for other things. Okay, and as we've seen, this property probably doesn't hold, right? So like if we go up to a high threshold, it sure looks like we're asymptotically dependent over here, and it sure looks like we're asymptotically independent over here. Okay, so this model probably doesn't do everything we need it to. Okay, so here's what we're going to do. We're going to do something very similar. So in a way, this sort of like combines the Camilo Castro paper and the Hazard paper. So we're going to say, okay, we're going to use this marginal transformation to heavy tail. So we're going to let this Gaussian process be on equal footing with this other part by transforming it to have heavy tails. We're going to have this spatially varying tail weight parameter that's going to allow our tail dependence to vary over space, and we're also going to build this scaling factor out of compact kernels that's going to allow scale separation. So if you're in a compact kernel, you're going to have asymptotic dependence. If you're far enough away that you don't share a kernel, you're going to have asymptotic independence. Okay. And it's all great to say that, right? So we sort of intuitively can figure out a way to construct this model, but we also have to be able to say something about it. It's just sort of really difficult to come up with analytically tractable forms that let us have expressions for these chi coefficients and let us, do some analysis on these models. And it turns out the sort of key to doing this is mixing Levy random variables. Here's how this is going to work. So we're going to have W is a compact kernel and S is a Levy random variable. And so what you're seeing here is we're going to put knots at these pluses, and then our compact kernels. So this is just the compact kernels at one location, and the radius of the support of a compact kernel sort of like determines how big our sphere of asymptotic dependence is going to be. So we can estimate that, right? So the idea is that if we're standing here and we have a kernel and it doesn't overlap with a kernel here, then we're going to be asymptotically independent. But if we're within one of these circles, we're going to be asymptotically dependent, potentially, right? We can always tweak this parameter phi and make ourselves always asymptotically independent. So the key to making the analysis work is picking a convenient distribution for these mixing, these things we're mixing, these SKs. And it turns out Levy distributions are really convenient. They're a subclass of alpha stable distributions. And the key thing about them that makes this easy is that they're closed under linear combinations. So here we have linear combinations of these S's. Okay, so we have linear combinations of Levy random variables. We sort of know what the answer is, and we can tell exactly what the tail weight is. The other thing that's nice is that they have Pareto-like tails. Okay, so this is a heavy-tailed random variable, so we can modulate it to sort of fight with the transformed Gaussian process to see who wins, and who wins depends on oh, it's not here, on the exponent phi. Okay, and so let's say, yeah, I don't want to say a whole lot about this, except that the marginal distribution from this process is really important, because remember, we're doing our Copula approach. It's sort of lost from way back in like slide 2. So we need to be able to transform from this process to some other margins. Okay, and it turns out because of the analytical tractability of these Levy random variables, we can actually do this. So we can write down what the margins look like, and they're messy, but we can write them down. Okay, so we can do this transformation. More interesting is the dependence properties. Okay, so as I said, if we're far enough apart that we don't share compact kernels, then we're always asymptotically independent. But suppose that we're close enough that we do share a compact kernel, then what does the dependence look like? It all depends on the phi, and this phi changes from location to location. So if we're looking at location I and j, if both of them are bigger than 1/2, then we have asymptotic dependence, and we can write down the dependence. If they're both smaller than 1/2, we have asymptotic independence, and we can write down this thing eta. Eta is called the residual tail dependence coefficient. So this is useful for measuring the subasymptotic tail. So how quickly does that chi decay to wherever it's going to decay to? So we can write down exactly what the subasymptotic tail looks like. And in the case of both phis smaller than 1/2, we get asymptotic independence, and we can tell how strong that is. What if one is bigger and one is smaller than 1/2? Then we also get asymptotic dependence, it turns out, and we can write down chi we can bound chi. We can't write it down explicitly. Okay, and so the analysis is a little bit messy. This picture is a little bit messy. So sort of ignore the gray curves for now. But what we're seeing, what I want to convey here is this is the colors of the surface of phi. So phi sort of determines the potential for dependent strength. So in this red regime, phi is bigger than 1/2. So if things share a kernel in the red regime, they're asymptotically dependent. If they share a kernel or not in the blue regime, they can never be asymptotically dependent. So for example, locations 3 and 2 share a kernel and they're in the red regime, so they're asymptotically dependent. 3 and 1 are both in the red regime, so they're potentially asymptotically dependent if they share the kernel, but they don't share a kernel, so they're asymptotically independent. And everything in the blue is asymptotically independent with everything else. And so the goal is going to be to estimate this phi surface, which you may think is kind of a tall order, but it turns out we can do it. Okay, and so how are we going to make this work? we're going to build this phi surface out of essentially Gaussian processes, and maybe we have a correlation model in that Z in that Gaussian process that's non-stationary, which is going to be important. So we have ways in the literature of modeling this non-stationary for a Gaussian process, so I sort of remember in the beginning I swept under the rug this issue of the marginal distributions. Well, the theory tells us that if we use block maxima, so in the case of precipitation, maybe we take the biggest daily reading of our rain gauge over a year or something like that. So the asymptotic theory tells us that looks like a generalized extreme value distribution. So that's what we're going to do. We're going to assume a generalized extreme value distribution and estimate block maxima. We're gonna use the probability integral transform to put our generalized extreme value observations y onto the same marginal scale as our transformed Gaussian process x, and this is going to be actually the most difficult part is this marginal transformation. It turns out we have to do some numerical integrals, but we can do it. Okay, and if we want to look at this as a hierarchical model, this is what it looks like. So our response y is GeV distributed. GeV is a 3-parameter family. There's a location, scale, and shape, and these can vary spatially. So I didn't write that, but they can vary spatially, and that's fine. So we'll transform our GeVy's into the marginal scale of x and model x as this this sort of like spatially varying, scale separated, transformed Gaussian process, which sounds like a mouthful, but it's actually, I don't know, to write it down, it's not that complicated. The spatially varying R is this weighted sum of Levy random variables where the weights are determined according to a compact kernel. And then our latent Gaussian process has some correlation function, maybe that depends on space. Okay, and we're going to assume independence over time. And this is actually really nice computationally because it allows us to parallelize the likelihood across time. And you can kind of believe this, right? Like these are block maxima, so you can believe that the annual maximum from 2022 is independent of the annual maximum from 2023, or at least maybe conditional on some large-scale climate variables or something. Okay, but anyway, it's computationally convenient to parallelize. Okay, and so here's a bit of a simulation, and so we have a couple of things spatially varying here. This is the phi surface. Remember, this is the thing that controls the weight of the local tail. So this is the phi surface we're simulating. This is the rho surface. So this is the thing that controls the correlation in the Gaussian process. And here's just a picture of the data, and the kernels, the compact kernels, are in red. Okay, so we do 625 spatial locations, 68 independent replicas. So this would be 68 years. So why 68? Because we have a 68 core processor. So this is sort of like maximizing our computational resources. Okay, so we fix the GeV parameters. This is a heavy-tailed process. So this would be 0.2 is like what you'd see in precipitation. Okay, so we run MCMC. Oh, sorry. Oops. So we run MCMC, and you can see how long this takes. 144 hours. That's 6 days. Okay, so this is not a quick thing to fit. Here's just an example of one posterior surface from one of these draws. So here's a draw of the phi surface, and this is the posterior mean of that surface, and you can see it's actually capturing it, I would say, pretty well. I was worried we wouldn't be able to do anything here, but it looks like it's doing reasonably well. And of course we get credible intervals for the surface too. Yeah, so what about the non-stationarity in the latent Gaussian process? Well, here's the simulated surface, and this is the posterior mean. So that also, I would say, looks pretty good. So there's a lot of spatially varying stuff in this model, but at least in simulation, it looks like we can actually fit it. You'd worry that it wouldn't be identifiable, but it looks like it is. So here's a coverage analysis, and this is from 20 runs. This is very expensive, so 20 runs is not enough to do this right, but here we are. And so what you're seeing is, so this is the phi, it just location 3. Here's the phi location 6. So it sort of looks like it's estimating it well, possibly well-calibrated credible intervals. So this is just showing that, well, if you treat your credible intervals like confidence intervals, how often did they cover? And this is saying, well, okay, if we have a 95% credible interval, it's covering it. I don't know what percent that is, but pretty close to nominal rate. So this is just showing that, well, the MCMC is sort of estimating things the way we'd hope it is. So it's doing okay for at least these local phi's, also for the local rows. So this is the Gaussian correlation, doing a pretty good job. At least it's not obvious it's not doing a good job. And then here we're estimating the radius of the compact kernels. Okay, so how big of a sphere of asymptotic dependence do we want to allow? And so that also looks like it's doing okay. Okay, and so as you can see, this is not finished work. So we're ongoing with the simulations. Something else you may worry about as well: does the number of knots matter? So maybe we're going to try to figure that out. Does the location of the knots matter? Can we move the knots around? Can we estimate that from the data? Maybe. Maybe we make this non-stationary further, even more non-stationary, in that maybe the radius of potential asymptotic dependence varies from location to location across the country. So that's something we could think about. Yeah, so lots of interesting directions to go here. We're not done. And so yeah, so just to summarize what we did here. The joint spatial tail of a process like precipitation or any other environmental process, there are these subtle characteristics that are actually pretty important to be able to capture if you want to do risk analysis well. How high do I build my levees, right? This is practical problems that all depend on sort of the tail dependence. And these differences can be subtle, hard to diagnose with exploratory data analysis. And it's really hard to build models that are flexible enough to accommodate all the sorts of behaviors we might want to be able to capture. But these transformed Gaussian scale mixtures seem to be able to do it, as long as you kind of allow them to vary spatially and to have this scale separation. Can we do local asymptotic dependence, long-range asymptotic independence? Okay, so mixing heavy-tailed random variables seems to be a way into it, and the levy construction makes the analysis tractable. I mean, it's still a little bit difficult, but it's tractable. And so so we get the full matrix. So all these features we wanted, and as far as I can tell, it's the first time we've been able to do that. Okay, thanks. That's it.
Yeah, action. I have one question. The model that you written down could accommodate non-spatially varying scale.
Yes,
It could.
if that phi surface were flat, which is allowed. Yeah.
So what if you do that a priori? Could you specify that? But you perhaps speed up the computation. It took what, 144 hours?
Yeah. So if you look, just trying to find the model. Yeah. So if you look at this, if you made this a single number, this would be very similar to the Camilla, Castro, and Husserl model. The only difference would be this transformation. So yeah, totally. You can make that a number instead of a surface, and it would be much easier to fit. Although I should say the rate determining step is actually that marginal transformation, because you've got to do that numerical integral at every location at every MCMC. So it's incredibly slow. That's the thing. So it's not this isn't the problem. It's the marginal transformation that makes it so slow.
Great talk. So, we are both familiar with this extra smoothing with low-rank approaches. So, what do you see here with the low-rank approaches? Do you see extra smoothing or something like that?
Extra smoothing
in the estimation of the surface intensity.
I don't think we have enough experience to know. Basically, these pictures are all we have. So it's certainly possible that there's certainly possible. But yeah, I don't know enough to be able to answer that. Yeah.
If the marginal transformation is the problem, could you just construct a set of tables and look at it?
Yeah. Yes. So our previous version of this, without the spatially varying stuff, we sort of did exactly that. we constructed it. It was lower dimensional because nothing's spatially varying, and so we just sort of did an interpolator. But this is 4 dimensions, and so we're actually working on this, but it's non-trivial to do it in 4 dimensions. To do it for this particular geometry. So yes, this is a very good idea, and we're working on that.
So earlier you showed how the inference we make on the hill dependence really depends on the threshold you choose. Does that come into play in this model at all? I might have missed that part.
Yeah, so this, this is a really important issue, and I've not even attempted to address it. So we kind of got around this by using block maxima data rather than threshold exceedances. So we're not actually fitting this to exceedances over a high threshold. We could. There are some technical complications with that, which we're working on overcoming. Turned out it's much easier to fit it to block maxima, but you end up with the same issue with block maxima. I'm picking 1 year maxima, but that's sort of arbitrary. I could have picked 10 years or 5 years or 3 years, right? So this is another version of the threshold problem. And so, yeah, we just do 1 year because it's precipitation, right? But we could have done 2 years, 5 years, and we might have gotten different results. So this is an important issue that we haven't really thought too carefully about.
You mentioned one of the issues with one of the Husserl papers was this expansion in terms of a finite number of compact exported basis functions. And your model also has some version of that. Can you talk a little bit more about how those are different or why the issue one is other than the other?
Yeah, so the point I was trying to make was just that they get spatially varying spatial dependence, but it's only spatially varying in this sort of, it's okay. Wow. Really complicated. Yeah, so you have your compact kernels, right? And you combine them. So maybe you get a whatever surface like that. So this would be like 5S. And so it's not constant, but it's only not constant because there's only a finite number of kernels, right? So it's, I mean, you can claim it's non-stationary, but it's not in a particularly useful way, right? But that's not what we're doing. We're having a whole separate process to estimate phi of S. So our phi of S is like a Gaussian process. So it's fully flexible in that sense.
Any more questions? Yes. I think there are some results on trivial activation using MCMC. I wonder if it would be easy to do the prediction of the conditional tail probabilities. Not sure if you cover that part as well.
Yeah, so at the end of the day, well, I don't know, maybe this is what you want to do. You want to do prediction. I'm not sure if the important risk analysis question is a conditional probability or it's probably a marginal probability, I would say. Like in the future, what's the probability of enough water falling over this watershed to overflow my dam? And yeah, so that all just sort of comes out in the wash with the MCMC. You could also do conditional prediction with the MCMC. And that would just be like a Kriging surface. Except it's not Kriging because it's this extreme, it's like an extreme value version of Kriging based on this model. Yeah, so you certainly could do that.
If there are no more questions, let's thank our speaker.